What if the reason we have never heard from intelligent life in the universe is not because it doesn't exist, but because the universe itself makes contact between civilizations almost impossible? Think about the scale of what we are dealing with. The universe is about 13.8 billion years old. It contains hundreds of billions of galaxies, and each of those galaxies holds hundreds of billions of stars. Around many of those stars are planets, and a fraction of those planets lie in the so-called habitable zone, where conditions could allow life to exist. Even if intelligent life is extremely rare, the sheer size of the universe makes its existence statistically likely somewhere. And if even a few civilizations manage to survive and evolve millions or even billions of years before us, they would, in theory, be far beyond anything we can currently imagine. Their technology, knowledge, and understanding of physics could be so advanced that our own civilization would look primitive in comparison. They should have already solved problems that we are still struggling with today. So the question becomes unavoidable. If intelligent life is likely and advanced civilizations should exist, then where is everyone? Why haven't we seen them? Why haven't they contacted us? Why is the universe so silent? The answer is not what most people expect. It is not that extraterrestrial life is absent. It is not that civilizations are hiding from us. And it is not a lack of curiosity or intelligence. The explanation is far more fundamental and far more restrictive. The laws of physics themselves seem to prevent meaningful interstellar travel and contact. This means the silence we observe may not be evidence of absence, but evidence of limitation. The universe is structured in a way that places strict boundaries on speed, energy, and time. These boundaries are not technological hurdles waiting to be solved. They are built into the fabric of space and time itself. A common assumption is that advanced technology can overcome any obstacle. If a civilization is intelligent enough, patient enough, and resourceful enough, it should be able to travel anywhere, even between stars. This idea feels natural because it reflects human progress. We have gone from flight being impossible to sending spacecraft beyond our solar system. But the leap from planetary travel to interstellar travel is not just a matter of improvement. It is a completely different category of problem. Because at cosmic scales, the limiting factor is not engineering skill, but physical law. To understand this, we first need to grasp the scale of space itself. Distances in space are so large that we measure them in light years. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second, the fastest speed anything in the universe can achieve. Even at that incredible speed, space is vast beyond intuition. The nearest star to our sun, Proxima Centauri, is about 4.2 light years away. That means its light takes 4.2 years to reach us. If we sent a signal there, it would take 4.2 years to arrive, and any reply would take another 4.2 years to come back. A single conversation would take nearly a decade. And that is just the nearest star. Most stars are much farther away, and the average distance between stars in our galaxy is about 5 light years. The Milky Way itself is roughly 100,000 light years across. Even light takes 100,000 years to travel from one side to the other. When we expand further, the scale becomes almost incomprehensible. Our nearest large galaxy, Andromeda, is about 2 million light years away, and the observable universe stretches about 93 billion light years across. Even light needs billions of years to cross it. At this point, the universe stops being simply large and becomes something closer to unreachable. Because there is a strict physical limit, nothing with mass can travel faster than light. This is not a technical limitation. It is not something better engines or better materials can fix. It is a fundamental rule of reality, described by Einstein's theory of relativity. As an object moves faster and faster through space, time itself begins to slow down for it. This effect, called time dilation, has been measured and confirmed repeatedly. As you approach the speed of light, time slows dramatically. At 99% of light speed, time passes about 7 times slower. At 99.99%, it slows even more dramatically. At the exact speed of light, time effectively stops from the perspective of light itself. But here is the key point. Anything with mass cannot reach that speed. As you accelerate, your energy requirements increase, and so does your relativistic mass. The closer you get to light speed, the more energy you need, until reaching the speed of light would require infinite energy, which is impossible. So even in theory, no spacecraft made of matter can ever reach or exceed the speed of light. And since stars are measured in light years, this creates a hard boundary. Interstellar travel is always slow compared to cosmic distances. This is where the paradox begins to take shape. If the universe is full of intelligent life, why does it look so empty? And why does physics seem to trap every civilization within its own star system? The answer may lie not in who is out there, but in what the universe allows to happen at all. This is where the problem becomes more concrete. Because even if we accept that nothing can travel faster than light, we still need to ask a deeper question. What happens if we try to travel as close to that limit as possible? At first glance, it seems at least partially workable. If a spacecraft could somehow reach 99% of the speed of light, then nearby stars might become reachable within a human lifetime, at least from the traveler's perspective. Due to time dilation, a journey that looks like several years from Earth might feel shorter on board the ship. This creates the illusion that interstellar travel is difficult, but not impossible. But the illusion breaks once we look at the energy required. To push even a small spacecraft to relativistic speeds requires enormous amounts of energy. Not just large in everyday terms, but beyond anything a civilization like ours can currently generate. The faster you go, the more energy you need, and the relationship is not linear, it grows dramatically as you approach light speed. To understand this, imagine trying to accelerate a 1-ton spacecraft to 99% of the speed of light. The energy required would exceed the total energy consumption of human civilization by tens of thousands of times. That is not a small engineering challenge. That is a planetary scale limitation. And this is only the beginning of the problem. Even if we assume a highly advanced civilization with access to far superior energy sources, fusion power, antimatter, or something beyond our current understanding, the scaling problem does not go away. It only shifts. Because you are not just accelerating a ship. You are also accelerating its fuel, its shielding, its life support systems, and everything needed to keep it intact during the journey. This is where the rocket equation becomes unforgiving. The more fuel you carry, the more fuel you need to carry that fuel. The system grows exponentially until it becomes physically unmanageable. So even with perfect technology, the universe imposes a cost that grows faster than any civilization can realistically pay. And even if energy were not a limitation, another problem appears immediately: time. Time is not just a background setting in physics, it is part of the structure of reality itself. And in interstellar travel, time becomes one of the most brutal constraints. Let's say a spacecraft somehow manages to travel at 99% of the speed of light. From Earth's perspective, a trip to a nearby star might still take several years. From the traveler's perspective, time slows down, making the journey feel shorter. That sounds like a solution, but it creates a hidden cost: separation from everything you left behind. Even a journey to the nearest star system means that by the time you return or even send a signal, years or decades may have passed on Earth. Relationships, societies, and entire generations can change in your absence. The traveler does not simply move through space. They move into the future of their own civilization. Now expand this to the scale of a galaxy. The Milky Way is about 100,000 light-years across. Even at extreme relativistic speeds, crossing it would take tens of thousands of years from the traveler's perspective, and far longer from the perspective of the galaxy itself. At that point, interstellar travel stops being an expedition and becomes a civilization-scale project. No single human lifespan can contain it. No single generation can complete it. It would require self-sustaining ships that survive across thousands of years, possibly tens of thousands. And that introduces another problem: stability. No human-built system has ever remained functional without failure for even a fraction of that time. Machines break down, materials degrade, software fails, radiation damages electronics. Biological systems evolve unpredictably. Over thousands of years, even small errors accumulate into catastrophic failure. So even if physics allowed the travel, the engineering of maintaining life and machinery over such immense durations becomes another near impossible barrier. But the universe is not done yet. Because even if we solve energy and time, there is something far more dangerous waiting in the emptiness of space itself. Space looks empty from a distance, but it is not truly empty. It contains sparse gas, dust, and high-energy radiation moving at extreme speeds. And when you are traveling near the speed of light, even the smallest particle becomes a potential weapon. At everyday speeds, a grain of dust is harmless. At relativistic speeds, it becomes something entirely different. Imagine a tiny particle so small it is invisible, colliding with a spacecraft moving at 99% of light speed. The energy released in that single impact can be comparable to a bomb explosion. Not because the particle is large, but because the relative velocity is enormous. Now multiply that by the reality of interstellar space. A spacecraft traveling for years would encounter countless particles, each one carrying destructive energy. Even sparse hydrogen atoms become high-energy impacts. This turns space into something closer to a minefield than an empty vacuum. To survive, a spacecraft would need heavy shielding, but shielding introduces mass, and mass requires more energy to accelerate. So the solution to one problem directly worsens another. Radiation adds another layer of danger. Cosmic rays, high-energy particles originating from supernovae, black holes, and other extreme cosmic events constantly move space. On Earth, we are protected by the atmosphere and magnetic field. In space, there is no such protection. Over long journeys, radiation damages electronics, disrupts systems, and harms biological life. Even advanced materials degrade over time under constant exposure. So now the picture becomes clearer. Even if a civilization could build a fast ship, it still has to survive an environment that actively destroys anything trying to move through it. But even all of this still assumes something important, that you are trying to travel within a reasonable part of the universe. Once we scale up further, the situation becomes even more extreme. Everything we have discussed so far applies to traveling within a single galaxy. But what happens when we try to imagine crossing between galaxies? The nearest major galaxy, Andromeda, is about 2 million light-years away. Even at near light speed, such a journey would take millions of years from an external perspective. From the traveler's perspective, time dilation reduces it, but it still represents tens of thousands of years of continuous survival, maintenance, and system stability. And this is assuming nothing goes wrong. At this scale, failure is not an exception, it is expected. The probability that every system, every component, every biological or artificial process remains functional across such time spans becomes extremely low. And then there is the final barrier, causality itself. Because as distances grow larger and time spans stretch further, communication becomes increasingly meaningless. A message sent today might arrive in another civilization long after it has evolved, changed, or disappeared entirely. In effect, the universe prevents any real-time interaction between distant civilizations. So even if intelligent life exists everywhere, each civilization may be permanently isolated inside its own bubble of space-time, not by choice, not by secrecy, but by the structure of the universe itself. At this point, the silence of the cosmos begins to make sense. It is not necessarily empty. It may simply be unreachable. And that leads to a difficult but powerful conclusion. The absence of contact may not be evidence that we are alone, but evidence that the universe is fundamentally built in a way that keeps civilizations apart. So when we put all of this together, the silence of the universe starts to look less like a mystery and more like a consequence of physics itself. If intelligent life exists across the cosmos, it may still never meet, never communicate, and never even detect one another in any meaningful way. Not because it does not want to, and not because it does not try, but because the structure of space, time, and energy places strict limits on what is physically achievable. We often imagine advanced civilizations as unstoppable, capable of bending the universe to their will. But the reality may be far more constrained. No matter how intelligent a species becomes, it still exists inside the same physical laws. The speed of light remains the ultimate boundary. Energy requirements still scale beyond practical limits. Time still stretches across distances in ways that break continuity. And space itself remains hostile, filled with particles and radiation that turn long journeys into survival challenges. Even if a civilization reaches a level far beyond ours, mastering fusion, antimatter, artificial intelligence, or forms of engineering we cannot yet imagine, they still cannot rewrite the foundation of reality. They may improve efficiency, extend survival, and push boundaries further than we ever could, but they cannot remove the boundaries entirely. And this leads to a striking possibility. The universe might be full of life, yet still completely silent. Not because life is rare, but because contact is physically suppressed by distance, time, and causality. Every civilization may be trapped inside its own cosmic horizon, separated not by intention, but by impossibility. In that sense, the universe is not empty, it is divided. Each intelligent species could be evolving in isolation, building its own understanding of reality, perhaps even asking the same question we are asking right now, wondering if anyone else is out there, staring into the dark, receiving no answer. And if that is true, then our situation becomes even more profound. We are not searching a quiet universe. We are searching a universe where silence is expected, because communication across it may simply not be physically feasible. So the question shifts one final time. It is no longer just, are we alone? It becomes, is the universe designed in such a way that no one can ever truly find anyone else? And if that is the case, then every signal we send, every probe we launch, and every message we broadcast into space is not just a search for others. It is also a statement of existence, a way of saying, we are here, even if no one may ever be able to respond. Perhaps that is the true meaning of our exploration of the cosmos. Not guaranteed contact, but persistence in the face of silence. Not certainty of discovery, but the refusal to stop asking the question. And that brings us to you. If you found this exploration of the universe and its limits thought-provoking, consider subscribing for more deep dives into space, physics, and the biggest unanswered questions in science. Like the video if you want more content that challenges how we understand reality, and share it with someone who still believes the universe might be easier to cross than it really is. Because in the end, whether or not we are alone, the search itself may be one of the most important journeys any civilization can ever take.